Welcome, everyone. It's my pleasure tonight to welcome Xavier. And like Theo last night and Mina Hassman tomorrow, we stand on the same landscape in slightly different places, but looking in the same direction to the future. So we've known Xavier for a long time. He is an architect and an innovator, head of design for Hassel, and he's been leading computational design for at least 2 decades, especially within interfabrication and additive manufacturing. And he's done pioneering projects in extreme environments across the world and on the moon, an exploration of that, which we'll see today. Collaborated with NASA and ESA on sustainable space habitats. He's an expert in parametric design, one of the initiators of it, and he was the director, I think the founding director of Smart Geometry, which was, for 2 decades, he built this vast international network, which I and many, many other people who are interested in that field presented papers and went to. He's taught at Syracuse, University of Ghent, and the Bartlett, and spent a lot of time in juries and crits mentoring young architects of the next generation. So he has impactful work, and we're going to see Bidi Bidi tonight, a performing arts center in one of the largest refugee settlements on Earth, and the Moon projects, and many others, I hope. So please join me in welcoming Xavier.
Thank you so much for the introduction, Mike. It's great to be here. Important week, the climate week here at the AA. Does everybody hear me well? Yeah, just checking that. Cool. Yeah, let's get into it. Architecture at the edge, regenerative design from Bidi Bidi to the moon. I'm going to talk about a few projects today, and maybe a little bit introduction where I'm actually based. I'm based in London here in a company called Hassel. We're quite a large international global design firm based all over the world. But I have a small team here in London, and that's the innovation team. And what we end up doing quite often, we find ourselves designing architecture in extreme environments. And it can be anything from a refugee settlement to a glacier in Switzerland to the moon, even. And we find that really interesting because you really get tested when you design in these extreme environments. Because it's not quite often protecting yourself from environments and being sustainable within those environments is actually a way of surviving. It's not a nice to have anymore. It's a way of survival. So the 4 projects I'm going to talk about today is Bidi Bidi, Art and Music Center in Uganda, a NASA project we did for Mars. Then we're going to go back to Africa. We're going to Tanzania for Hope Village. And I'm going to finish off with a project we've done for the European Space Agency, which is a lunar master plan for the moon. So let's get started. Bidi Bidi Performing Arts Center. This is a project, rendering of it. I thought to give an introduction of it, I'll get the client to explain it, because you don't often have the client talking about projects, right? But this is quite a special client, so I'm going to give him the word.
Hey, what's up? I wish I could play. Really, I'm not good at all. But I know a lot of really great musicians in Uganda. Come check out what we're about to build for them. Let me tell you an amazing story. We went out with our foundation to Uganda to look for talent and to meet talent. And what we found was unbelievable. We met a young guy called Zex in Caribbean Records in a slum in Kampala. Pew, pew! That's Zex. Check them out. So what we did is we built a little recording studio. 5 years later, Zex has a #1 single in the country.
How you doing? Nature Son. Big up to the Shadowman family. We just made a new song in Caribbean Records about the youths, how we can motivate the youths.
Then we went out and visited a refugee settlement in the north of Uganda, Bidi Bidi. And we asked them what was missing and what would they like. They told us that they would love a center to be able to express their creativity. Very soon, we're going to break ground on this music academy that has recording studios, classrooms, an amphitheater. What I love about this project is we have a local community collaborating with international architects and engineers. Thanks, Hassel Studios and Arab. I can't wait to see how this is going to turn out.
Yeah, so that was Nax and the client of the TO Foundation. They funded the project. And let's get a little bit more into where this place is. This is Bidi Bidi refugee settlement. It's been for over 10 years now. And we have about 270,000 refugees living there. Lots of the refugees, we are about 50 kilometers from the border with South Sudan. So we're in North Uganda. And when you look into it, when you go a little bit closer, it's not a refugee settlement that I thought a refugee settlement would look like. I always thought it was going to be lots of UN tents and all that, right? It's not. It's actually kind of built by the refugees in local materials, in local architecture. And you might think this isn't very dense, but this is extremely dense if you think of it. Because a lot of the refugees are farmers, and there is basically no farmland, right? So although you might think this is not super dense, this is actually highly, highly dense population. Now, the site for this project is this one here. We're kind of on the south side of the refugee settlement. And, you know, the settlement has been around for quite a while. You have the UN operating there for education, they operate hospitals there and all that. They give food aid, medical aid. But one of the things that isn't there is a cultural place, a cultural center. And I always have to think about the fact that Bidi Bidi is 270,000 people and is about the size of the city where I'm from. I'm from Ghent, originally, in Belgium. That's about 300,000. If you think about it, all the things I grew up with, like a modern art museum, a design museum, we have opera, theaters, all these kind of cultural institutions that we have. And actually that is not there, you know, because that is not kind of provided by the UN. So, this is a project site. We are working with an organization called Sine Locata. Sine Locata is actually founded by refugees in the settlement. And they're doing two things. They are providing education in music and IT skills, and also entrepreneurial skills. Right. So it was with that organization, they were actually the client. They were not the fundraiser, they were the client. They will operate the center that we worked with over a period of about 2 years. This is a little drawing of the site where it is, where we're able to build the center. One of the things to kind of see is that borehole that we have there, right? There is no sanitation, there is no running water, there is no electricity in the center, right? So it's a very tricky place to build anything. And this is kind of on the middle of our site, is that borehole, which is, you'll see it later in my presentation why it's important. It's a lot of contaminated water that get pumped up there. So because there are no toilets and so forth. But also immediately looking at the local architecture, this is what you normally get. We've got these buildings that are often about 3 by 3 meters or 4 by 4 meters. They are mud constructions and quite often only used to cook in or to sleep in. So they're not really kind of, a lot of refugees kind of really live outside because the temperature is kind of that good to do that. So it's kind of quite a traditional way of living there. And things that we figured out quite often is electricity. Yes, there is electricity, but only with these kind of local solar panels. So there was no electricity net for us to kind of hook into, also for our contractors to build the center. as you saw, we had this kind of borehole, which is kind of, we thought socially was quite important to keep, because people would use it also to water plants and crops and all that. And we want to place our building on the site that it doesn't interrupt too much, right? So for that reason, we made a kind of a round-looking building, a curved building that people could really navigate around, but at the same time, people could navigate through. We thought it was quite important to make it as open as possible, to make this building as public as possible. It's a little model here of the building. I often get this question when people go like, oh yeah, but you're designing this kind of curved building, this kind of elliptical building. Isn't that a bit crazy to do it in a refugee settlement? Because it's really complicated to do, right? To kind of set out or construct a building with this geometry. Well, I think it's not. It's actually one of the easiest shapes to draw, because you can draw an ellipse with a piece of string and a pencil, and you pin it down in 2 points. And if you will stroke your pencil around it with that little chord, you literally draw an ellipse, because that's the definition of an ellipse. The distance of the point on an ellipse to the two centers is always equal. So this little trick, you can do that on site as well. So it was actually quite easy to start setting out this building, this quite complicated looking building, quite easily with literally 2 stakes in the ground and a rope. And this is the site when we started its foundation settings. It has also 2 centers. We kind of kept that idea of 2 centers in this building as well, although it's not geometrically the actual centers. These are the functions in the building. We had a music classroom where the music lessons were given. You can see that here. Now, operation. And we also had a recording studio, which was a little bit more complicated to design and to construct. I say here, some of the recordings happening with the local kids making a record. And of course, it has to be performance, a performance space. In the middle of that's really the center of the whole project, is that performance space. And this is actually just on the day it opened, it was kind of an impromptu dance that happened and performance that happened. And a little auditorium. And we knew that the money we had, the funding we had was enough to build a massive auditorium. So we made sure that it was, we could actually expand it to the back. So we created these doors that could open up the space, and for really busy times, the whole thing kind of opens up and people can really stream in and kind of enjoy the performances. Now, this is the geometry of the building. It has this kind of funnel-shaped roof. Now, that's for a particular reason, really, because we figured out, looking at the borehole that we had on site that had contaminated water, we thought, well, why don't we kind of, as we have this big roof, collect all the water, right? Collect it, filter it, and then redistribute it. And you can see it on the top left of the building, of the picture there, you see a distribution tank of the filtered water. We also positioned it in such a way that the tank with the water was actually down the hill from the center. So we didn't need to use any pumps or any complicated systems. It was really, really kind of just using gravity to kind of fill the big tanks. But we also wanted to make sure, we could have designed this building with just like a normal roof and a downpipe and kind of catch the rainwater there. But I wanted to make sure that people knew it. People saw it, that the architecture itself expressed that. So the building is really kind of has this funnel-shaped building roof that then you get in the middle, all the water gets collected, and you kind of see, we weren't quite sure if it was actually going to work, but it actually does work. So these are all these kind of gutters that kind of are in, there are also the roof structures, and they actually kind of like bring all the water into the center space. Again, it's a really complicated place to build. So you have to make sure you are able to construct it there, right? So we wanted to make a special building that looked different. That was placemaking, but we wanted to make sure we build it in a very with simple ways, with simple geometries. For example, the inner structure, that's just a hyperboloid. It looks very curvy and all that. But at the end of the day, it's just straight pieces of metal, just put in a particular way. This is my favorite picture of the whole project because we did not intend it to become a playground, but the kids seem to love it. And it's just a great picture, I think, on kind of, as an architect, when you design something, you're not always sure how it's going to be used, but this is kind of a really happy accident almost. So we have that big roof, and the big roof does quite a few things. First of all, it protects our walls, which I'll explain in a minute, because they need to be protected from the rain. And the roof, as you see, is set above about 1 meter of the space of the building, and it is also not insulated, right? Now, for performing space, right, the problem is if it would rain, it would be terrible because you will hear it will be like a drum. Right? We fussed about this for about 2 weeks. We're really worried about it. Oh my God, how are we going to do this? How are we going to insulate this for acoustical reasons? And then we jumped on a call with a client, senior locator, and they were like, because they will operate this center, they're operating it now. They were like, well, it only ever rains for 20 minutes. So we'll just stop the performance and we'll wait a little bit and then we continue. So it was our kind of like cultural misunderstanding that this was a massive problem, although senior locator was like, no, it's actually not a problem whatsoever. And it helped us as well because we made the roof non-insulating, so it didn't heat up that much. So when it heats up, the steel heats up, but we also figured out there's lots of, that's a solar analysis that shows how it's kind of shading the building. But we also figured out there was a strong southern wind coming to the site. So there's some wind analysis that we did here to kind of then see how that building could be naturally ventilated continuously, right? So a very lightweight steel roof that does, of course, heat up, but also cools down quite quickly. Now, this is a quite complex-looking roof still, right? As you can see here. So we had to do some geometrical rationalization of it to make this buildable. Luckily, I did spend about 15 years of my life, or a bit over 15 years of my life at Foster & Partners, where one of my tasks is to help design teams rationalizing projects like these to make them on budget and buildable. So it was always a trick on how can you make a curved building made out of flat pieces or straight pieces. That was really always a trick, what you had to do. And I worked for a long time under this man, Hugh Whitehead. He was my boss and really my mentor for many, many years. And it's one of he passed away a few years ago. But without his guidance and help and mentoring, I could have actually never done something like this, which was coming up with a geometry that looks quite complicated, but in the end of the day is actually quite simple. Because the whole thing was, how can we build this roof and the cladding of it, which is corrugated metal panels, who are all just flat pieces of corrugated metal. How can we construct that? Getting a bit technical now. I know that a cone, right? If I take a cone, I can subdivide it in flat quadrilateral pieces, very easy to do. If I chop the top of the cone, nothing really changes. If I then actually skew that cone, like I've done there, nothing much changes either. All the panels will also stay flat. So what that roof surface really is just an inverted version of that. So I knew before we went to site, we did a whole computational model of this project. We knew every single piece was going to be flat and actually really simple to fabricate. And this little axonometry of that project showing all the kind of like panels that we had in there. Now, just to prove it was possible, some side shots. These are the trusses of the roof structure. Now, those were all made in Kampala, which is about a 9 hours drive. And you might think, well, this is a steel structure, 9 hours drive, not exactly locally made, right? The reason why we chose this, and we didn't choose to have a wooden roof, which I wanted for sustainability reasons, regenerative reasons I wanted to do originally, is because we looked also at the social impact. Right. First of all, we have 270,000 people living there who use wood as fuel for cooking and all that. So there is already a lot of, let's say, unrest in between the host community, Uganda, and the refugee community. So we thought we're not going to add to that. Right? There's lots of deforestation happening because of that around the refugee settlements. So we thought, like, okay, it might not be a good idea to actually now add to that issue. So we did decide, although it wasn't probably the most sustainable from a pure environmental perspective, from a social perspective, we thought it was actually much better to kind of stick with a steel roof. Right, you can see that here. All of this was, of course, computationally designed. Each of these beams are different, prefabricated in Kampala, together with our local architect, Local Works. But there's another part of the building, and there's really two big parts: is the roof and the walls. And the walls here are made by bricks. Now, we chose to use non-fired bricks because to fire bricks there in Uganda, you would also need to have wood to have energy for your fuel for your ovens. So we decided, okay, let's not use fired bricks. So what we did use was compressed earth bricks. We do have some cement and lime in there, but a limited amount, and they're all compressed by hand. The great thing about this is that you can also use the locals to help with constructing this, right? Because it's quite a manual task where 50,000 of these bricks had to be made. So, and what was fantastic about the bricks was that we decided to only create one type of brick. There was one brick, one geometry of this brick, but this brick had to do lots of things, right? And you can see it has a certain pattern in there, right? And the pattern does a few different things. First of all, if you have it on the outside, you open up the brick so it actually lets in natural light. We don't need to buy windows. And then you see on the back, you see two different patterns. You see on the left-hand side, on the corners, you see it opening up. Well, that's actually to absorb sound because we're in the recording studio, by the way. So in the corners, we created something which is called a Helmholtz resonator. It opens up the bricks, and inside is an absorption material, a natural absorption material that we put in the bricks, in the cavity. And in the middle of the wall, you see the bricks sticking out. Well, that's actually to diffuse the sound. So we worked with Arab on this, with our acousticians, to kind of come up with this kind of perfect kind of pattern for the bricks. So how are they made? So, well, this is the brick press. This was we exhibited this in the London Design Biennale. So we kind of got one of the presses over, but it's much better to get Victor, who's one of the founders of Cinelocator, explaining how it's been done on site.
Right behind me is a heap of soil that is used to make the compressed earth blocks. So this soil is excavated underground. It's used to make the compressed earth blocks that will be used to raise the walls of the building. So right now here is the process of making the blocks. A very complex way of making it neat and clean.
Okay. And here you see these bricks being used in the music classroom, right? You see there we have mainly a diffusion pattern happening. And this is then in the finished recording studio. The recording studio was interesting because it was the only room that we wanted to have a ceiling. All the other rooms don't have a ceiling, right? You just have the big roof hovering on top of it. because here we want, of course, kind of not have outside sound coming in, but we still want to have light. So we came up with this kind of interesting idea, and we worked with a local architect on this one, which was embedding these kind of glass bottles that were just cut in two and then welded together and then actually put in the concrete in the casting. So that actually brought us kind of these natural light points into the building. Now, a project like this is quite complicated to do, you know. I think, you know, we went often to BDBD, particularly the local architect, of course, Felix, and it was important to constantly kind of have connections with the local stakeholders. So that was us kind of like presenting the final design to the local stakeholders, but like local organizations, but also to the local host and refugee community, right? Because both these communities are actually present there. And we actually presented to the guy who used to own the land. So he was actually, his land was bought by the government, right? And he was then given a new piece of land, and he was actually kind of really proud of it, which we were quite surprised by in the end of the day. So yeah, this is us kind of like explaining the project in the refugee settlement and working here with Marwa and Sylvain of Sinolocata, local organization, and of course with Local Works is there, which is a local architect and also contractor of the project. We did a lot of mock-ups as well, as you saw, of the brick wall, but also the roof construction. This is in Kampala, actually, at the local architect's site, where we kind of signed off the final mock-up of the project. And it was also important to kind of continuously, you know, because we're very used to using technology and all sorts of computational methods. We thought, well, we use it for really expensive projects in capital cities around the world. We're going to use the same tech, right? So this is us bringing our HoloLens to the site with Marwa, who was able to see what the building will look like. This was before we actually broke ground, for him to see what the building would look like, because they will be operating, have been operating for the last year and a half, the project. Okay. Going somewhere completely different now. This is what we did quite a few years ago, Mars habitat for NASA. And funnily enough, I always think it might feel such a jump, right? To kind of go from a refugee settlement to Mars. Well, for me, the projects are quite similar in a weird way, because you do need to think about sustainability also on Mars, as you do in a refugee settlement. And it's always about looking at your environment, what is around you, what is the environment that you're dealing with, even how extreme it is. So how you start a project like that, right? So look at the environment. Mars, what do you do? Well, first of all, it's far away, right? So every kilogram you're going to bring there is going to be very expensive, right? Again, in BDBD, we also worked with local soil. So we didn't actually bring material from very far, except the roof. So again, here we're going to have to work with something that is quite local. And what else is there? Well, it's quite cold. It's about minus 50 average. There's a CO2 environment. There's 1/3 of gravity. And the worst thing is there's radiation, lots of radiation. So we need to protect our astronauts from that. Now, the best way to do that really is a cave. The best way to kind of protect astronauts is a cave, because what you want is mass around you. Because the problem that we have on Mars, that we don't have on Mars, is that we don't have a thick atmosphere, because it's 100 thinner than on Earth, and it's also not electromagnetically charged, which means radiation on Earth is actually where we have electromagnetic fields, gets deflected. Doesn't happen on Mars. So we need to protect our astronauts, and the best thing is with mass caves. We don't know where the caves are. So we're going to design our own cave. So this is actually the idea of this project, is that we have this kind of shell structure, as you see, this little cave that we built. And underneath there, we have this inflatable unfolding bubble. The bubble in the middle is made on Earth, brought from Earth. And the outside, we're going to make with local materials, like we did on BDBD. And we're going to use local earth. Well, there's no earth. Can't call it earth. It is called regolith. It's called Martian regolith. So the idea is that we construct first our cave, our shell structure. And as you can see, this is done by lots of small little things. Well, those little things are little robots. So we had this idea to come up with a robotic system that would 3D print the shell structure layer by layer, probably over a few years' time. And the geometry of this, again, is not that we drew it, we generated it, right? Because we wanted to have a structure, a shell structure that works under compression only. So we can make it without reinforcement. It's just 3D printed regolith, Martian regolith. Now, when we say we're going to 3D print it, we also wanted to design those 3D printers. Although we haven't made them yet, we did design them. We came up with this idea of diggers, printers, transporters, different types of robots. And some of these are quite realistic, like the one on the right-hand side is actually based on an existing type of digger that NASA has been developing. And then I got this render through from our visualizer. I loved it. I will always use this render. But I was a bit shocked about one thing, and that is this in the corner here. Because our visualizer thought, oh yeah, that's kind of cool, this kind of 3D printing process. But what happens when the robots are done? Well, they kind of, it's like a boneyard of robots. That's it. They've done their job. They're all dead. And that was terrible, right? Because think of it, we make a machine, it does one thing, and that's it. It's a really terrible idea. So I thought back to the drawing board. So we redesigned the robots. And we came up with this system. It's an autonomous robotic system that is modular. And it's built out of, it's basically like a Lego system of robots. So you can kind of take a wheel, take a digger, take a battery, take this, and actually take a printing bit and start making your own construction robots. I'll show that a little bit here, where you kind of have different combinations are possible of the same robot. Now, of course, we haven't completely built that yet. This was just a concept, but I think it's important to start thinking like that if you design something that will need special machinery, that you actually start thinking about this in such a way. Now, you might think, well, that's all a bit sci-fi, isn't it? Well, I think it's not really, because the way we design these kind of futuristic things is that we always take existing technology that is there, right? So there is already research happening on Earth where we use regolith style materials, where we look at how can we kind of bind that together, how we can fuse it together through microwave technology or sintering technology. And so there's lots of research already happening on that. So we just kind of take that idea and bring it further and bring it 10, 20, maybe 30 years into the future. And that's the 3D printing of that Martian regolith. So, project exists out of this shell structure. And underneath we have these inflatables all prefabricated on Earth, brought to Mars. And there's 6 of those interconnected parts. So what we have there is, I think we have a living space, we have a lab, we have a greenhouse, but geometrically, they're all quite the same. They're all the same modules. They're this kind of radial system of modules that is interchangeable. So you could actually make a lab into a greenhouse, change it back into something else, because you want to have that adaptability when you're building on Mars. So this is one of those racks, and the way the racks actually work, I don't have a video on that here, is that it's actually a much more efficient system compared to what we currently have on the International Space Station. Because I'm not sure if you know, if the International Space Station has lots of corridors, and on the walls you have all the science racks. But what you get is like astronauts will do something on a rack and then they move on to somewhere else. So actually spatial optimization is really bad because you just have lots of space in front of racks, which is not always used. You just get loads of corridors, right? Here we have these racks that is movable. So they actually kind of open up, you can go in, do what you need to do, and then close it again. And that same system actually happens for the greenhouse and for everything else on the base. But it's kind of this radial organized system. And this is, for example, the sleeping area where we have a hollow deck, and the gym, of course, as well. Now, we'd like to think a little bit in detail about these things as well. And I like to think one of the things when we were putting our people in the renders, we were thinking, like, what are they going to wear? Because if you look at the ISS, everybody wears like an overall. I thought it would be a bit more interesting and also a bit more realistic. Because at the moment, I'm not sure if you know that, but astronauts in the International Space Station, they wear their clothes. Once they're dirty, they don't wash them. They actually get discarded in a module, so with all the other trash. So they just wear constantly new clothes. That's what they do. Right? There's no washing in space. We thought there could be a better, more sustainable way of working. And we thought, well, why can't they make their clothes out of existing fabrics that they have? And they might have that. Because this is how we land stuff on Mars at the moment. I think this was a Curiosity rover landing on Mars, looking back while it's landing, look at the parachute that it lands with. So we were thinking, well, that's material is only used once, should be used a few more times, right? So why wouldn't our astronauts in the future make clothes out of it? Luckily enough, I knew a guy who does that. This is Chris Rayburn, good friend of me now. And he has a fashion label, Rayburn, that actually always looks at that. They take overstock of material, existing materials, parachutes, all sorts of material, and actually make clothes out of that. So we worked with him, and he lent immediately some of the pieces they did before. And of course, we can then fashion our astronauts. It's not an astronaut. This is Chi, which was our interior designers, modeling here to then be placed in our, hopefully, a quite realistic vision of what it would be to live on a Martian base. One place, this is quite an important bit, because this is the workshop, right? And a workshop, lots of things will break. Lots of things will need to be fixed. So this will be a crucial part, is having material there. This is kind of the Martian Fab Lab. On the left-hand side, you see a 3D printer, a Delta printer. You see some sewing machines. You see some other bits there, so people can fix stuff. Right? It's really, really important, especially when you live for a longer time on another planet. I said at the beginning, it's very expensive to bring anything to Mars, right? Every kilogram you're going to bring is going to be quite expensive. So I always say pack light and compact. Well, if you look here at the living space of the base, that's not very compact, is it? And particularly the furniture, right? Doesn't look very compact. Well, the reason they look like that is that we didn't bring them. We're thinking of actually making them on Mars because we will have waste material. We'll have waste plastics, probably from science experiments, from food packaging, and so forth. So what are we going to do with all these plastics? Well, let's start reusing them, right? So let's start thinking about reusing and recycling materials much, much harder here. So, so for this, we collaborated again. We collaborated with Nagami, and they're based just an hour outside Madrid. And they designed for us certain furniture that would actually fit within that Martian base. This is all printed with PETG's plastics. So, and you see that was a kind of a chair that we then were able to use within our architecture. Now we like to. The interesting thing about working in a really technical field like this is that we should never forget we're architects. Right, I think design is such an important driver. So we have our base designed, but we also want to have a view out. It's really important for the for our astronauts. So this is the famous cupola view in the International Space Station. It's great for the astronauts to look out, but it's also a weakness. It has to be protected for radiation and for debris coming in. And how do they do that? Well, it actually has these flaps. It's a very mechanical engineering way of looking at it. It has these flaps that kind of close the cupola when something is coming, or we have to close it for radiation protection. So how are we going to do that? Because we do have windows as well. Well, we thought, well, we're not going to use a mechanical thing. We're just going to use an architectural thing, and that is a courtyard. Right? So a courtyard is a great thing because in a courtyard, you don't get direct sunlight. You have indirect sunlight, but you do get light in. The same thing on Mars. We want to have indirect light in, but we don't have direct light because direct light is radiation coming from the sun. So it's actually really, really harmful. So for that reason, we designed our little courtyard. So we still have views out and views into the other spaces of the base, but all our bubbles are actually protected from direct sunlight from the sun. So we used some solar analysis tool, but we had to trick it a little bit to kind of make sure it was based on Mars, because of course all the parameters were based on Earth, right? So I had to trick it a little bit to make it right. And you can see that here in a model that we have, that we built of that. We're really lucky though doing this project because the timing was absolutely perfect. Because at the end, just at the end when we finished the project, there was an exhibition happening in London. It was called the Moving to Mars exhibition in the Design Museum. We were invited there to kind of actually go and build one of those inflatables. So great, it's a great way to do it. It's a really great way to test it out if it would work. So we have a big inflatable there. We have all the 3D printed furniture there. And in the background, you see that big window. And we had a big digital screen, all built. The whole base was built in a gaming engine, so it was kind of interactive as well. So if you, as a visitor, you went there, you could go sit there, hang out, and actually see the changes happening within the base. You could see the light changing. You see other astronauts across, and really knew what it would be like maybe to be an astronaut on Mars. Okay. Jumping again. We're going to Tanzania. But again, I think about it, about the project I explained, it's always thinking about reusing materials or also using local materials and kind of how you kind of do that in the best sustainable way. New Hope Village, Tanzania. This one is not built yet. We're still looking for funding. So I'm going to drink a bit of water first. So this project is outside Dar es Salaam in Tanzania. It's a really important project, Hope Village. It's a project that aims to have a permanent safe home for vulnerable girls in Dar es Salaam. So there are about 200 girls that are now living with a person there that kind of takes care of them. There's an organization set up around it. But what we really want to do is actually build a whole master plan around this. The master plan would have housing, would have education, but also would have this community hall that connects back to the local community. I can give a whole talk about this project really, but I'm not going to do that. I'm going to really talk about the architecture itself a little bit. This project is a collaboration again between Hassel, EAC, Institute for Advanced Architecture of Catalonia, EOC engineers, and the One Heart organization. Each time you do a project like this, it's really important to connect locally, right? It's we're based in London. It's a really terrible idea to think that we can just sit here and design something locally. One Heart is a local organization though, and the first thing we thought to do was to kind of understand the local construction technology, right? What can be built, what can't be built. So we sent Edouard. Edouard is teaches and is a professor in EAC in Barcelona. He's a fellow Belgian as well. And he was up for it. He said, like, I'm going to go. I'm going to go for 2 weeks and actually go everywhere and check how everything is constructed. There's local metal roof structures that's being done. He walked around with a contractor as well. Says concrete is being used as well. This was one of the contractors' projects, and lots of local timber roof structures. Right. And an interesting thing about the timber roof was, because we were really interested in kind of using a sustainable material. We thought, well, there's a lot of local timber fabricators, and there's a lot of local stock. The issue is that it's all quite small timber sizes. So the sections are quite small. The reason for that is that there's a lot of export of the larger timber goes to the Middle East and to China. So we were thinking, okay, so we're kind of stuck with smaller pieces. So what are we going to do? How can we build an interesting architecture? We build something fantastic that is really placemaking that could work. And inspiration comes out of weird places, right? Mine came out of this. It's a 70s trivet where you put your hot pan on, right? This kind of little, but when you lift these things up, they're a bit floppy, right? Because they have these pieces of wood and they're strung together with little metal rods. And we made a little model out of that, trying to see, well, maybe that could also be a roof, because we wanted to create a community center for this project, for the master plan, and we need a large span architecture. So playing around with this, of course, I'm modeling it, working with EOC engineers on this to create what we call like a wooden blanket. It's a tensile structure, but uses small discrete elements of timber. Now, it was really great working with EOC engineers, to be really honest. Actually, O'Callaghan, they're actually presenting this project today in a big engineering conference in Mexico at the moment, probably as we speak. Because they also made physical models, which I love. Like if the engineer is the one that makes the physical model, it's actually really, really interesting. This was actually exhibited in an engineering exhibition here, not far from here, actually, last year. And you see this kind of like timber pieces. We have a rod going through it, and then also spaces. We're not quite sure what these spaces are going to be, but we hope we can find a local material to do that as well. You can see that here. I could go into technical details of this, but I'm not really going to do that because it becomes quite complicated. But the way the project is built is around this kind of central, I'm going to go back to slides, this central spine. So it has a central metal spine, and from that spine, you do get these kind of that wooden blanket hanging. We do need to then have some larger structure on the sides to kind of put it under tension as well and keep it in that shape. And the trick was because the space is a big communal space on the left-hand side, and on the right-hand side, we'd have a kitchen and a bakery and other small spaces. So much smaller spaces we needed, so a lower ceiling. So for that reason, we have this big spine that then kind of bifurcates into two smaller spines, and you can see that I think here. So it kind of drapes over the lower building there. So kind of that's how we kind of create in one geometrical system, kind of two kind of architectures, I think. Then the roof we talked about, there was also the wall. Again, we wanted to, because we just finished Bidi Bidi, we wanted to make sure that we use some local material. So we thought, again, let's use local earth to build with. But EAC was at that point doing quite some interesting research in earth 3D printing. So we thought, maybe this is an interesting thing. So maybe we can use earth printing. So this is the research that was happening at EAC in Barcelona. We can use earth printing, and in a particular way, that it also let light in and lets ventilation of the building. So together with the students and the staff there, we designed these walls that could permeate the light, and also the wind goes through it. So we have ventilation. And whenever we do a project like this, I think it's really important to go and prototype it. In particularly also for funding, both this project and the BDBD project, we were continuously, and we still are for this project, trying to find funding. So we're helping the client to find money to build this project. And a great way to do that is by making great renders, beautiful renders, and physical prototypes, because suddenly it becomes real. Right. And people that will fund this project that just need to put money into a render, right? Once they see that it's being built, that is possible, it kind of, creates some trust each time. We definitely, for this project, we also have the plan, and working with EAC as well on this, is to, once we've built it, that we kind of leave the printers there. So we kind of educate and people locally on how to use this technology to kind of be able to kind of continue constructing with it. We did the same thing with the presses as well in BDBD. The one that you saw was actually a third press that we bought to show at the Design Biennale. The other two are still in BDBD and being used. And this is kind of the idea how we imagine construction going to happen. Probably not in that quite order, but having a very simple WASP 3D printer, which is a very simple system really, for the walls 3D printing, and then this kind of spine, the central spine, that is quite a simple structure, and then from that we get these kind of wooden slats being hung or wooden blankets, and then of course in the end you get corrugated panels to finishing off the roof. So, going back to space. So it's kind of interesting to kind of jump in between both of these places, of course. For me, it's quite natural to design in such a different environments. So this project is for the European Space Agency. It's not on Mars, it's on the moon. A lot of the issues that I have on Mars, you also have on the moon. So you also need to protect yourself for radiation. Just trying to see how I'm doing timing-wise here. Am I all right? Yeah. So this is a master plan, really. It wasn't just a base that we've done previously for like 6 to 10 astronauts. It's a much larger project. And I did this project because we wanted to kind of... made a mistake before. I made a mistake in 2 projects, I think. One project did at Foster's, the other project did at Hassel here. The one on the left is a lunar base we did many years ago. On the right is the Mars project that you see. But for each of these projects, at the end of the project, I did this thing where I thought like, oh, imagine how it grows, right? So imagine if I have one pod, one building, and then we do more, we add in more to it. I did it twice. It was for the video or for the render. But that's not how something like that grows. You need to plan for it. You can't just say, oh, it's just the same thing over and over again. It doesn't quite work like that. In construction phasing, it also wouldn't quite work. So we took that as an opportunity for this project to think of a master plan of how you would actually design from the beginning to be able to expand this system in a really proper way that is realistic. We often look at other extreme environments, and one of a good one to look at is Antarctica, right? McMurdo Station in Antarctica, which is not a really great example, right? Because it's kind of ad hoc constructed and added to it. Now, people didn't have a big master plan for it. There's better examples, I think, which have a kind of a master plan. This is Halley 6 in Antarctica. The British Antarctic Survey has been there for quite a few years now. And that project, I really love this project. I didn't do it myself. And it's an interesting idea. It actually has a master plan really behind it. Modules, how they come together, it's expandable and all that. So we were thinking, what are we really doing? We were really doing is we're designing a master plan for the moon. That's what we're doing. Because I do believe great cities like Barcelona have really interesting master plans that allow for adaptation, allow for change, and allow for the unknown future of how it will grow. Because we don't know what will be on the moon. We don't know who will go, what kind of industries will be there, what a lunar economy will be like. So how do we plan for that? So this is our base setup. We designed these kind of pill-shaped inflatables, quite similar to what we had on Mars, but a bit different. Now, the problem is if you have lots of buildings, lots of modules connecting to each other, because you can't just go from one building to another, right? You can't just kind of step out on the moon. Doing a spacewalk takes days to prepare on the ISS. It's incredible complex thing to do, to go outside. So most of the time the astronauts will be inside. So every space needs to be connected to every other space. The problem with that is it's a bit like having in a street where you, if you want to go from one house to the house on the other side of the street, that you need to walk through every other house. You don't really have a street. It's a bit weird, isn't it? So we thought, let's design for that. So we designed these kind of skywalks. So they kind of see the blue ones, the light blue ones, and they're 2 levels above. So those actually kind of connect straight through from one point of the base to another point of the base. We actually have 3 levels, because when you connect everything to everything, it's very difficult to get out in the outside as well. So we have 3 levels. We have the bottom level is where we have all the spaces are connected to each other. We go 1 level up. This is where you can get out. You can get a suit on through a suit port, or you can get in a rover and get outside. You see that there. And then the 3rd level up is where you can actually go through from one part of the base to the other base without having to kind of go through all the other spaces. So kind of complicated system, but kind of quite simple in a way as well. So it's all built around these kind of inflatable modules again, because, you know, it still has to be light to get to the moon. We decided on this geometry and not a circular or radial one that we showed on Mars, because we learn each time. Each time we do these kind of space projects, we tend to kind of do better than the one before. And we have these pill-shaped geometries. And the reason for that is that, it's a curved geometry, which is good because you have to take up a pressure difference, because of course you have a pressure of the humans living in there. Outside, it's a vacuum. So it's a pressure volume, right? A sphere would be the best, but that's really hard to kind of plan in. So we designed it with this one because these pill shapes, actually in the middle, you can quite regularly start space planning it out. It's actually quite a simple way to kind of lay this out. We figured out this kind of 27-meter one because we did lots and lots of testing, and we are able to kind of fit out in many, many different ways. Anything from labs to greenhouses to recreation, even to sports facilities for team sports. So that was kind of our kind of, let's call this our grid almost, you know, that's our base module in how it can be fitted out in many, many, many different ways. You know, and looking always when we do a project like this, even if it's a master plan, we love to kind of go a little bit deeper and a bit more detailed, even if it's in one little spot or 2 little spots. And this is one spot. This is like the standard astronaut room. There's a few weird things in that you might not spot on the ISS. You see, for example, veneer, right? We believe that it's actually quite important to have some natural materials around the astronauts. We learned that from talking to people at Halley 6 on Antarctica. I had a great conversation with the commander of the station, and he told me this story where they said, we were kind of unhappy with the cold and all the plastic around and all the rubber. So they decided to take some of the crates they had, the plywood crates they had for shipping some stuff, and they used that and dismantled it and put it on the wall, right? Because it made them much more comfortable and much more cozy to live having some wood around you, right? So we're even thinking maybe we have bamboo, right? So this is bamboo. We actually spoke to quite a few people how it is possible to grow bamboo as well, because it's an interesting material because it grows so fast. So maybe bamboo veneers, maybe using bamboo to construct with is an interesting one in space as well. So thinking about lots of kind of details immediately as well at the same time to kind of understand what the look and feel would be. And the base that we designed was for about 144 people, which is Dunbar's number. A sociologist who kind of looked at how big a community needs to be or how large it can be before it actually starts to socially kind of fall apart a little bit. So with 144 people, everybody knows everybody still really, really well. So that was our idea about why 144 people. We designed a lunar bar because with 144 people, it's going to be a bar, right? People have a bar, we need entertainment. And again, looking at some details, so yeah, they probably might reuse some old engine parts, right? To maybe create their little tables. There's some 3D printed furniture there as well, yes. And this might not be possible because it's a kind of a museum piece now. Of course, this is the seat of an old lunar rover of the Apollo era, and also we can design really, really light furniture. Look at that, how light this furniture is, because you can do that because you're on the moon. And the bar itself, the drinks, we're not going to bring glass bottles, are we? Because that's going to be so expensive. So we have the drinks, so just hang up in little bags. And we'll use these bags later to then 3D print maybe the furniture. So just kind of like, designing this with some clues and with kind of trying to think how it would be to live there and having to reuse and recycle all the materials that you have. And of course, not knowing what this base will be. We designed it for, a crew of 6, but it could grow to 144. We have an idea how it might go, but we don't know. We don't know if it will be tourism that will drive a base like this. It might be research or commercially. So we didn't really design a base. We redesigned just a master plan for a potential lunar economy. Now, we do still need to protect our astronauts from this radiation. I spoke about that. And so we need that shell structure, that kind of cave above it. And we're looking at other research, and other kind of architects have done similar stuff. Here, Block Research Group, the Armadillo on the Venice Biennale, we found really interesting and beautiful. But one of the things that we realized was how difficult it is to do this, how precise you need to be with everything to kind of make all these blocks that are slightly different. So we started to looking further and think, isn't there another way to do it? Isn't there a simpler way to do it? Because I know, having worked with 3D printing, concrete 3D printing as well in the past, how complicated it is and how tricky it sometimes is and to be accurate. And we really didn't believe that accuracy and precision is something we're going to have on the moon. So we thought the opposite. Looking at the group pavilion from Cora Diericks, where she just uses kind of little spiky elements to aggregate together to make structures. Of course, looking at the UE pavilion from a few years ago and the Venice Biennale, this is all made out of salt. So well, this is interesting. And this really looks like these coastal barriers where they stop erosion, these kind of hexapod systems, these are tetrapods. And we started to think, why? Maybe we built with those. Maybe we built really rough and randomly, so we don't need accuracy. So we can maybe just throw elements on top of each other, right? And somehow they will, if you do it in the right way, they will create these structures. This is using Houdini and some computational techniques to kind of start testing that. It goes twice. And this is the overall idea we had. So to create these shell structures, we probably need to start with some foundations because there's a lot of kind of forces going on that. Again, make it with these kind of hexapod systems. And then we need our support structure. We need scaffolding. It could be a big, simple inflatable. Not one where the people would live in. It's just a kind of a construction inflatable. And on top of that, we then start placing more and more of these hexapods. And we're even thinking, well, maybe we're not going to place them. We have 1/6 of gravity on the moon. So maybe we'll just throw them, right? So it might be easier to throw something. It might be quite accurate because they have wind. So we can probably precisely think on how we throw these and actually use the fact that we're on the moon in our construction process. Building these kind of little inflatables underneath. And then even having more of these hexapods piled on top of it under an angle. So it's actually self-supporting. to create more protection for the astronauts. So a completely different way of what we had on Mars projects, where we were printing layer by layer. Here we're just kind of placing these kind of discrete elements on top of each other, and kind of, immediately always testing out physically. I think it's important, even in practice, to do this. Once you've done it digitally, just do it physically as well. This is us just buying like a ball on a yoga ball on Amazon, to be honest, some wood, and actually start testing it straight away to see, does this work or not? Kind of worked. And then some more kind of stop motions here of us testing it out in the studio, sometimes throwing, sometimes placing it under an angle again, and also then buying some inflatables to do more tests. There we go, little inflatable. It doesn't need to be much. You're just kind of starting to kind of test things out as soon as we can. And then we had a larger one made that was exhibited here in the Royal Academy for the summer exhibition. So yeah, it's a bit of a whirlwind through 4 projects, I think, that each of them look at sustainability and kind of reusing material and using local materials, because this, of course, for this project, we would be using local lunar regolith, right? Of course, we're not going to bring all these parts from Earth, and and thinking about how it's not a luxury. Right, it's not a luxury to protect your astronauts from the sun. Right, protecting the astronauts from the sun is life and death, really. So, doing these projects really gave me a kind of another attitude by looking at projects that I would do, in London and other places, where sustainable approach is just not a way just to, a nice to have. It is life and death sometimes, like in these projects. One project I haven't kind of shown, and I mentioned I was going to talk about it, Mike, is that I love to teach, and I love to teach small children as well. So we did this project a while back, because a couple of years now, where we are with young kids. They're about, how old were they? About 11 years old. And we think about the future, right? This is thinking about the future, designing for the future. But we didn't have them to design on the moon or Mars, but we had them to design in their own area. It was a school in Walthamstow where I live. So we had them to design for a future where climate has changed, where there are extreme environments. Right, so we gave them three options. I think it was Walthamstow is flooded, Walthamstow is full of snow, and really, really cold, and Walthamstow is super, super dry and nothing grows anymore. So, and now design your own house or your own school within that environment. And it was incredible to do that, because they took it extremely serious, really serious for 11-year-olds, and we gave them all the options. We gave them some technology that is out there. And it was incredible to see that, how these kids were able to take tech and ideas and have visions of that. They used lots of AI. They drew a lot. They used AI to do that and all that. It was an incredible project. And it gave me lots of hope, right? Because, my generation, your generation, we all architects will actually change this world, but also generation coming after, they are actually kind of hopefully also well equipped to continuously think about designing in this way, no matter where it is, in a refugee settlement or on the moon. Thank you.
Can you tell one more time about lightning for Mars project? Like how it's gonna be?
About the Mars project? What
Like,
particular?
Lights, like electricity.
Electricity, how that was. Okay. Yeah. I didn't.
Oh, at the end, I'm sorry.
Yeah. There is so it's energy, right? It's a big issue, right? To get energy, like satellites and all that they work on, they always work on really small amounts of energy. So it's a huge issue. For the Mars project, we had a double system. We had solar panels, like farms of solar panels. The problem with Mars is there's two issues. Is you're further away from the sun, so the sun is less strong, right? It's one issue. Second issue is on Mars you do have something that are kind of Martian storms. So a storm that happens on Mars can happen over the whole planet, right? And what happens then is that you get lots of fine dust in the atmosphere. So it actually creates a kind of a haze around the whole planet. So that actually stops from sun getting to the solar panels, right? So it's two issues. Still, it's an option. And you also use nuclear energy. So NASA is working on kind of compact nuclear systems to bring with them to the moon and to Mars. So that's most of the two options that you often have in on other planets. Yeah? Yeah. That's three there.
Okay, so I have like two questions.
Mhm.
One is about the the Moon one. Basically, did you do tests of like actually how precise coverage the like those like the like I don't know how to call it the
Hexapods.
The
They're called hexapods, yeah?
how precise do they coverage from radiation do they provide? Because I could see that in your tests, like obviously they were like much more smaller scale. Like there were like micro, like small holes that were actually like kind of fully see-through, and that would be a big problem, right? Because there would be like points of constant radiation.
Okay.
So how did you test for that?
Yes, good point. There's two things to look at that. One thing was that we thought if there is holes, we could actually use loose regolith to kind of cover it. Right, so that was one of the ideas. If we have lots of holes, we have a structure, it's a stable structure under which the astronauts can go and build, and then we kind of drop loose regolith on top of it. The other thing is to think about it like this, is that you can't protect yourself for all radiation anyway, right? There's secondary radiation. If you go out, you also have radiation. So it's not like that you have one hit and you're dead. It's not how it works. So it is about how much radiation you get over time. If there are some holes in it, that's kind of okay, right? One of the strategies that we also have is that you see, for example, this is a good slide. You know, the kind of like the walkways that go from one part to the other part of the base, they're not protected, right? Why is that? Because you don't spend that much time in it. You just walk through, you maybe just a few minutes in there. Another thing is that some of these domes are thicker than other domes. If there is a solar event happening and there's a solar storm happening, you get a few minutes and then the astronauts know they need to go to one particular location, the base, which is more protected. So it's all about, managing that on how much radiation you get over how much time. It's very different if you're going to go there for 3 months, 6 months, a year, and all that. The age also kind of is an important factor. So there's different things on how to manage it. So you don't need to be continuously always protected. Right.
And my second question was kind of both here and the Mars. How much actually like realism did you put into thinking about like the habitats themselves when it comes to like, actually the construction of like, for example, those inflatable like spaces? Did you actually like approach them with like really huge level of like expectations of realism, or was it much more like on those idea stage when it comes to actual like technology of those inflatable spaces?
I think it's both really, because we go into I didn't go into super much detail because the inflatables are kind of a very particular system that we developed. They're called tensority system. There's tension elements in there as well. So we do go into quite a lot of kind of structural thinking around it, but also how these spaces would be used, right? Like, for example, on the base, one of the interesting things that we did was we spoke a lot to astronauts and also to people, Arctic explorers and people that live on the Arctic and overwinter there. And we ask them loads of questions. That's the best input to get. And one of the things that we wanted to understand from them, one of the things that we got from them is the fact that they like to have control over their own environment, right? They like to control that. Also where they have food, for example. So as an example, on our lunar base here, you have places for the astronauts themselves, and they get like a small little kind of, they can make a tea, for example. They have a boiler and they can make something very, very small. But then every 6 astronauts have a small kitchen, right? So they can make a half decent meal. But then there's also a bigger canteen. So they can actually choose where to have food and kind of have more control over their own life, which we think is important because astronauts' life is actually, well, commercial astronauts now, professional astronauts, they have, I think it's like a 10-minute slot. They know exactly for the next 6 months what they're going to be doing in every 10 minutes. So to give them control and freedom is actually really important. So we hope to kind of embed it in how we kind of structure these spaces. Yeah.
Okay. I also had 2 questions.
Not everybody 2, please.
The first one is again about the moon project, and actually I was curious about, did you take into consideration of earthquakes or like moonquakes that can be happening by the impacts by meteorites and etc.?
So meteorites is, when you look at the moon, right, it's full of craters. And you always think like, oh my God, it's going to be a crater every minute almost, right? No, of course not. You know, craters are still quite rare. The craters that you really protect for are micrometeorites. So they're very, very small. They can do some serious damage, but it's not that you're kind of protecting from massive boulders coming down. That is just, the statistics around that is almost, you know, it's almost, you can't really design for that anyway. You know, it's like the same thing as designing on Earth that a massive meteorite is going to hit you on your head. It's the same thing. You know, it's very, very rare. You don't need to design for it. For micrometeorites, you do. All right. Moonquakes, yes, that does exist, but they are extremely, extremely small. So it's actually kind of not that necessary to design for that.
And the other one is about the Mars project. I would like to ask about the first renders. It was just one cave, and the other renders were like a bigger
oh yeah,
cave
well spotted. Well spotted.
Yeah.
That's true.
Are you thinking of like a colony between these structures, or like how are you going to improve it into a bigger scale?
Well, the Mars project was actually just done for 10 astronauts, I think. 8 to 10 astronauts, I think. We didn't kind of go further on that. We decided just to do, that was designed for that. The lunar project here is actually the idea to go for much larger. So we probably, if you would want to kind of expand that Martian one, you probably have to redesign it slightly. You know, haven't done that yet.
Thank you.
Hi, I have 2 questions as well.
Is that a thing here? Everyone has 2 questions?
Sorry. The first one was when you were covering the base for the Mars one, you used the hexapods.
Yeah.
And I was wondering, for example, you talked about the wave dissipating blocks and how you got that from that. And I just thought, why not tetrapods or all these other forms that can like really click together well to form a structure? So why would it be hexapods? That would be my first question.
Okay, no, good question. We tried a bunch of them, right? We tried different geometries, mainly, well, a bit physically and a bit digitally as well. The main thing was, interestingly enough, was how stumpy they get, right? The stumpier they get, the kind of like how thicker the legs are and shorter they are, the more coverage they get, so the less holes you get, but the less structurally they are, the less they kind of interact with each other, right? So the thinner and longer they are, it kind of structurally is better, but it actually has less mass. So it was kind of a, you know, if we do this for real, this will a lot more research go into it, what that actual geometry would be. But at the moment, we thought that kind of worked well, that we still get enough interlocking and still a lot of kind of mass to cover from radiation. So it's kind of a balancing act there.
And my second question would be, when you were designing the rooms for the astronauts, you talked about how you recalled on your conversation with the Halley 6 commander and what they did with the wooden crates and how you wanted to bring that element of nature into the room. And you talked about how that translated into like designs further down the road in other projects as well. And I just wanted to hear a little bit more about that.
Well, more Earth-related projects. Well, I think It's an interesting project that we're doing at the moment, which is in South London, in Sutton, and it's a wellness center on top of a co-working space. And it was actually by showing the Mars project to the client there that they came up with the idea to build that extra extension on top of the building only with existing materials, only with materials that have already been used, so upcycled materials. So we're working on a project like that now. So keeping in mind this idea that, you know, if you are on Mars or on Moon, you're going to reuse materials many times over, or objects many times over. So we're working on a project on Earth here in Sutton, in South London, that actually does that. So the steel structure comes from an existing building. So everything is really reused in that project. So yeah, so that's the first test for us to kind of do that for real here as well. Oh.
Sorry. If it's okay, I just have one question. I really appreciate the care that is taken in all of these projects in resource optimization. I really resonate with the bitty bitty one, for example. But I wanted to ask, do you think it's a productive use of human and design resources in terms of the cost that goes into a lunar and a Mars project? And for example, how much of the New Hope Village in Tanzania could have been built with that same resource cost? Yeah, your thoughts on that if possible.
Well, yeah, of course, but that's always a client, right? So I need to pay my staff. So I would love to kind of spend my whole career building BD projects and all that. But, you know, somebody has to be able to fund it. We have to find ways to do it. BD we actually did pro bono as well, that project. Interesting thing about resources is that I think using computational design is an interesting way of doing projects like this. So BD was, because it was pro bono, we had to do it with a very small team. And it was myself and one, or sometimes two architects who were great designers, but were also great computational designers, right? So they were the whole package, really. So for that reason, we were able to do it with a really small team, and also working with a local architect who was actually really good. It was that connection with the local architect that was super important. They were really tech savvy as well. They always used the Revit models. So working with them together. Another thing that what we did is where we didn't lose time in redesigning, right, is that the local architect also became the contractor. That was a really important thing, that we had local architects became contractor, and we were able to design really detailed really early in the process because we're using computational design. So every single brick was a script that we used to design every single brick. So we didn't have to come up to later in the stage of the construction where we said, oh yeah, it doesn't quite work, right? That almost didn't happen. So we were able to kind of super early on work really efficiently and work with a local architect from day one, because we knew working with them what the local construction techniques are and how can we design, right? So embedding that into that whole process was actually quite an efficient vertical integrated system in that way. So that is something I think I learned a lot from that project that I want to apply to more projects. More highly integrated teams is really important.
Great, thank you.
So thank you. It's great there's so much interest. There's going to be wine served upstairs in the bar, and Xavier will be up there, and we can continue the conversation over a drink in the bar. So please join me in thanking Xavier for a fantastic presentation.